Well, first I would like to thank the organizers for inviting me here. I will talk about asymptotic dynamics of a population density with a model with a survival threshold that I will explain it later what it is exactly. This is a joint work with Pierre, and Takisukanis. Well, we studied the Darwinian evolution of a structured population where every individual is characterized by a parameter representing a phenotypical trait. The phenotypical trait could be, for example, the length of the giraffe's neck or the shape of beaks of Darwin's finches. We consider the dynamics under selection and mutations between the under mutations and competition between the traits, and we consider only rare or small mutations. So to see the effect of mutations, we consider large time behavior of the dynamics. We study the large time behavior of the dynamics, and what we expect to observe is what we observe in nature, phenomena like speciation, extinction, and branching. Well, first I will talk about a model with a model with without any survival threshold, and I will tell you why we need to add a survival threshold to the model, and then I will talk about the model with a survival threshold. Well, here is a model that we study. This is a model with a single nutrient. Here X represents a phenotypical trait, T is time, and N is the density of the trait X. I1 is the pressure exerted by the population on the resource. Actually, we suppose that we have just one resource and every individual is using this resource with a different rate psi of X, and so we can consider it as the total consumption of the population. And R is the growth and death rate of the trait X that depends also on the environment, and the Laplace term here is represents the mutations, and the epsilon is a small parameter. The epsilon in front of the Laplace term, it means that the mutations are rare, and the 1 over epsilon here comes from a change of variable in time, t to the t over epsilon. It means that we consider large time behavior of the dynamics. And we studied the limit of this, the solution to this equation when epsilon goes to 0, and we expect to observe that an epsilon 1 converges to a sum of direct masses. It means that one or several dominant traits will survive and other traits will go extinct. So this is a simulation of this model with this R here. Here horizontally is the trait, vertically is time, and the color is the density. And this is for epsilon small. So as we see, we have like something like a Dirac mass that is evolving in time. This is a dominant trait that is evolving in time. And here is the density at this time, and we see that the density is similar to Dirac mass. So to study the limit, we do a change of variable, and epsilon 1 equal exponentially epsilon 1 over epsilon. And well, under some assumptions, we can, under some reasonable assumptions, we can show that after extraction of a subsequence, u epsilon 1 converges to a continuous function that is a viscosity solution to this Hamilton-Jacobi equation with constraint. Here, I1 is the limit of I epsilon 1, and it is also the total consumption of the limit in the limit. And using this Hamilton-Jacobi equation and under some additional assumptions, we can show that weakly in the sense of measures, n epsilon 1 converges to a single Dirac mass. And this single Dirac mass is concentrated in a point that is a maximum point of U1, and it is a 0 point of U1. So this monomorphism is proved in the 1D case by Guibal and Benoît with some monotony assumptions on R, and in the multi-D case we have proved it with Alexander Lortz and Benoît under some strong concavity assumptions on R with quadratic behavior at infinity. Well, so in these cases we have monomorphism, and we can also give a canonical equation. a canonical equation refers to a differential equation that describes the position of the dominant trait. Actually, we can derive a canonical equation just formally in some with some strong assumptions. This is rigorous, but in general this is not rigorous and it is just formal. And we can compute it very easily just with differentiating with some simple calculations. First, by using the fact that U1 at the point of the mass concentration is equal to 0 and it is a maximum point, so we differentiate it twice and we have this equation, and then we also differentiate the Hamilton-Jacobi equation, and using these two relations, combining them, we obtain the canonical equation. But so if this was rigorous, then once we know U1 and I1, we can describe x bar of t. And if we know x bar of t, then N1 is equal to rho bar of t delta x minus x bar, as we said before, because it is a single Dirac mass in the point x bar of t, and rho bar of t is derived from this relation. So we have all the information for the limit, but the problem is that here this canonical equation is not rigorous. Actually, we are differentiating x bar of t, but we have some counterexamples that say that x bar of t is not even continuous. It means that we can have a jump of Dirac masses, but this is not realistic, because we don't expect that the dominant trait is has a jump, and we expect that it will evolve continuously. And we think that this is due to a problem in our model, that in our deterministic model we can have very, very small mass somewhere, but it doesn't mean anything because we cannot have less than one individual. But we don't consider this phenomena, and this very, very small mass can, if it is in a good zone, in a favorable zone, then it can grow up and create a Dirac mass and create a jump jump of Dirac masses, and this creates the discontinuity. And so this is the effect of stochastic demographic stochasticity. Sorry, that we don't consider in our model. And that's why we suggest to add a term in the model to consider this effect. So the model that we suggest is the model that we had before, but we add a negative square root term to the model, and this is to avoid the unrealistic tail in the problem. And here beta epsilon is a constant. It is a small constant that depends on epsilon, and it goes to 0 when epsilon goes to 0. And adding this term actually means that if n epsilon becomes less than beta epsilon, then this term becomes negative and more negative than this term, so the density will go to 0 at that point. It means that well, what we are looking for is that the traits that are represented by a density that is very low, it has to go to extinct immediately, and that is why we add this term here. So now I will talk about this model, and this is a joint work with Guibal, Bonaparte, and Tegis. So this is a simulation of the problem. At left we have the model without any square root term, without the threshold, and at right we have the model with the square root term, and the R that we are using is this function. So as we see, well, as before, horizontally we have the trait, and vertically the time, and the color is the density. So as we see that we have a jump in the Dirac mass in this case, but by adding the negative square root, we can avoid this jump and have continuous dynamics. So this model was first suggested by Benoît Pertin and Mathias Gauduchon in another model of population dynamics with local competitions when they had, and they in a model that with a competition kernel, and they added this term to the equation, and their numerical results confirm that the model with this square root term gives more similar results to stochastic simulations. For example, the evolution speed is much slower, and it is more similar to stochastic simulations, and the branching patterns are reduced, and they are smoother, and they are comparable to those obtained with stochastic simulations. So what we try to do is to study this model theoretically, and well, to study the model we had to simplify the model. So in the growth rate we don't have the term I, the resource term, anymore, and we have just a function r of x. So biologically it doesn't really make sense, but to do theorics we needed to do it, because already with this term it is complicated. And for the constant beta epsilon, we choose exponential of over epsilon, where is a negative constant. And some principal questions to be answered are, first of all, do this survival threshold change the dynamics? Because one could say that well, this term is with this exponential term is very small, and when epsilon goes to 0, it might have no effect, and that doesn't change the dynamics because it is very small comparing to this term. So a question to answer is that, does it really change the dynamics? And well, we will see it before, but we can show that in most of the cases, in general, it changes the dynamics in most of the cases. It's just some particular cases that it doesn't change. And also a question to be answered is, does the limit depend on the specific form of the survival threshold? It means that, can we replace the square root term with another power, and would it change the limit? And the answer to this equation is also that we can actually replace it with another form of survival threshold with another power, and it wouldn't affect the limit. So, well, for the theoretical results, actually I think that I don't have time to give the proofs, because they are technical and long, but I will try to give you the main ideas and also the difficulties, and then I will give you the main results that we have. Well, as before, we do a change of variable n epsilon equal exponential u epsilon over epsilon, and we put it in the equation, and we have this equation. So here, just formally, we can say that if u epsilon goes to something less than um, then this term is going to minus infinity. So we expect that u epsilon will go to, in this case, will go to minus infinity. Well, in summary, if u epsilon goes to something less than um, then it has to go to minus infinity. And if u epsilon goes to something greater than um, then this term is going to 0. So in the limit, we expect that well, this term will disappear, and this term will disappear, and we will have the Hamilton-Jacobi equation that we had before, dt of u equal gradient u squared plus r. So these are just formal calculations, and we can say that a formal limit of the function is this equation that is coupled with an open set omega, that is the set where the limit of u epsilon is greater than minus infinity. And actually in the set, in the interior of omega, u is greater than um, because if it is less than um, then it has to go to minus infinity, and also it verifies this Hamilton-Jacobi equation. So these are not proofs, they are just formal calculations, but one could a conjecture could be that this is the limit, and this is the this describes the limit, but it wouldn't be enough, because we don't have uniqueness for this equation. Actually, we can give a family of solutions to this equation, which are here for any r, any r. We can give this family of solutions that are the truncations of u1. u1 is the solution of the equation without any square root term, so it is the first part of the calc. And we can truncate if we can truncate u1 at eta and put omega eta equal u1 if u1 is greater than eta and minus infinity otherwise, and we can easily see that this is a solution to this Hamilton-Jacobi to this system. And so we have a family of solutions, and well, we would say that we expect that the truncation must occur at and not before, because we are not doing we are not putting anything for anything negative for the when u is greater than then it has to go to 0, and that it should not have any effect. So we would choose the solution which verifies the Dirichlet boundary condition. That means that in the boundary of omega it has to be equal to but again, this is not this doesn't give us the uniqueness for the equation, and we have some counterexamples that say that this equation is not can have several solutions. This is for r equal 1 and u0 equal minus x squared, and we can easily calculate that the solution without the square root term is u1. Well, the solution without the square root term is the solution of the Hamilton-Jacobi equation in all the domains. So that's why we can truncate it and just say that it verifies this equation. So that is why it is natural to say that it is a solution. But well, here u1 is the solution without the square root term, and well, a solution of the system is u1 truncated at as we said before, but we have also another solution, another viscosity solution to this system, that is the equation presented here. And actually we can prove that u hat, the second solution, is actually the limit of the u epsilons outside an exceptional set that is not very large. And well, easily we can verify that these two solutions are different. So I would like to open a parenthesis here and just say that here, if we accept that u hat is the limit, it means that the limit is not a truncation of u1. And as we said before, the mass will concentrate at the zeros of u, so the truncation wouldn't change the zeros. So it means that the zeros of u hat are not the same as the zeros of u1. So the concentration points have changed. So the dynamics have changed in this particular example. So we can already deduce that the survival threshold in this case has changed the dynamics. Now we can continue with what I was saying before. And one thing that we can verify is that u hat and omega hat verify the state constraint boundary condition. It means that I'm sorry, there is an this is wrong here. It's u hat is a super solution in omega hat and a sub solution in omega hat bar. This is the inverse, and this is equivalent to say that u hat is a supremum of this functional over all the trajectories that stay in omega hat. So it means that if this is omega hat, and this is a point x and t. The value of u hat of x of t is the supremum over all the trajectories that stay in the in the set omega hat, and they join it to point 0 y, and it doesn't touch the boundary here. It can just touch here, but not here, not here. It is like to putting minus infinity in the boundary. So actually, our conjecture is that the real limit is the solution to this Hamilton-Jacobi equation. So this Hamilton-Jacobi equation, we can see it as a Hamilton-Jacobi equation with an obstacle, because when it arrives at u equal then it becomes minus infinity. But the obstacle, it depends on the solution itself. And also, the limit verifies Dirichlet boundary condition and a state constraint boundary condition. Well, this is just a conjecture, but we cannot really prove it because, well, there are some difficulties in it. First, especially with state constraint boundary conditions, because actually the up to our knowledge, state constraint boundary conditions are the theory of state constraint boundary condition is not developed in time varying and non-smooth domains, and here we actually first of all obviously the omega here depends on the time, so it is time varying, and also it can be very, very non-smooth, so we cannot really use the theory of state constraint boundary conditions. So, and sorry, one thing that I forgot, that is this what does it mean, this conjecture? Actually, it means that if sorry, so if we have a set here where u0 is greater than um, then the set omega is the set of points x of t where there is a trajectory that joins x and t to a point z is 0, well, t and x to a point 0 and y, and this all along this trajectory the f is greater than um. The f that we have here, this functional is greater than um. So if there is a trajectory like that, then t and x is done in omega, and the value of u of t and x is the supremum of all these of this functional along all these trajectories which have this property. So this is actually a way of describing the limit, but we cannot actually prove, well, in some cases we can prove this, but not in general. But we can actually we use all these ideas that are behind the state constraint theory and this Hamilton-Jacobi equation, and we prove something that actually we prove that we have some upper bounds and lower bounds that are similar to this, but we cannot prove that it is exactly this. And so I give you the results that we have, and that's it. So in the case with R negative, in the non-positive growth rate, it is actually easier than the other cases, and we can show that the limit is actually U1 truncated, and we can easily verify that this function U verifies both direct limit boundary conditions and state constraint boundary conditions. And well, in this case, as we said, U is equal U1 truncated at um, and so the zeros of U are the same as the zeros of U1. So the concentration points have not changed, and the dynamics have not changed in this particular case. But in the general growth, with the general growth rate, we can just find some lower bounds and upper bounds for the limit. As I said before, it is something that is similar to this, but it's not exactly this. It's a bit complicated to define it. But in the case where R is positive, under some reasonable assumptions, we can actually show that these two bounds are equal, and we have the convergence. And in the case with R can take positive values, actually we can see that the solution is not U1 truncated. So the dynamics has actually changed. And well, for this I already have given you, I already gave you an example. And also the R proofs are by constructions, and the construction shows that the limit actually doesn't depend on the specific form of the survival threshold, and we can replace it by another power. And we can already see it, if this was true, then we are just actually cutting the trajectories at um, and it doesn't really depend how we have cut it with the model with an epsilon terms. So, well, I'm sorry, I think I don't have time to give the proofs. That's it. Thank you.